Welcome to this video. In the previous videos, we talked about why accuracy is often misleading, especially for imbalanced datasets. We then introduced precision and recall and how they focus on very different types of errors. In this video, we'll go one step further. We'll introduce false positive rate, explain how it differs from precision, and finally understand why ROC curves work the way they do, and what a good or bad model really looks like in ROC space. We'll also talk about precision recall curves, explain when they are more informative than ROC, and show how to decide which curve you should use for your problem. Are you ready? Let's go.
If you remember from the previous video, we had a model that determined whether a handwritten digit was a 5 or not. For each handwritten digit, the model assigned a score, essentially a probability, indicating how confident it was that the digit was a 5. After that, we set a threshold. Any score above the threshold was classified as 5, and any score below it was classified as not 5. Now, any digit whose score is above the threshold and is actually a 5 is considered a true positive. If a digit is not a 5 but its score is still above the threshold, it is classified as a false positive, which represents a model error. We also defined precision, which measures how reliable the model's positive predictions are. In other words, precision tells us, when the model predicts a sample as positive, how much can we trust that prediction? Another metric we defined was recall. Samples whose scores were below the threshold but were actually 5 were considered false negatives. The ratio shown in the figure represented our recall, which tells us how many of the real positive samples the model successfully identified. In other words, recall measures how good the model is at detecting positives without missing them, like how good of a detective it is. We also mentioned that recall is sometimes referred to as sensitivity, or TPR. Now in this session, we introduce a new metric, the false positive rate, or FPR. According to the formula shown in the figure, this metric measures the proportion of negative samples that were incorrectly classified as positive. In other words, the denominator consists of all samples that were actually negative, and the numerator represents those that were mistakenly predicted as positive. So FPR tells us, among all the samples that were not positive, how many did the model incorrectly raise an alarm for? In practical terms, it measures how often the system generates false or unnecessary alarms.
First, let's meet the false positive rate, or FPR. It measures how many actual negatives the model incorrectly flags as positive.
Let's briefly review the metrics together. First, precision. The denominator of precision includes all predicted positive samples. Its main focus is on the quality of positive predictions. The key question it answers is, how much can we trust the model when it predicts a sample as positive? Next, recall. The denominator represents the total number of actual positive samples. Its main focus is on how many of those positives were correctly identified. The key question it answers is, how many of the real positives did we successfully detect, and how many did we avoid missing? Finally, we have the false positive rate FPR. The denominator represents all actual negative samples. Its main focus is on false alarms. The key question it answers is, how many negative samples were incorrectly classified as positive? Back to our example. Let's see what happens if we lower the threshold. As we lower the threshold, many samples with lower scores will now be classified as positive. As a result, some false negatives will turn into true positives. However, lowering the threshold may also cause some true negatives to be misclassified as false positives. In other words, TNS decrease while FPs increase. Now let's examine how lowering the threshold affects key evaluation metrics like recall, FPR, and precision. When we lower the threshold, both TP and FP increase. Precision will decrease if FP increases proportionally more than TP. As we saw, any increase in TP comes directly from FN. Therefore, TP plus FN remains constant. In fact, the number of actual positives does not change, and as a result, recall strictly increases. An identical issue happens for FPR. Any increase in FP comes directly from TN. Therefore, the denominator remains constant, and FPR strictly increases.
So far, we've seen that our model assigns a score to every single sample. By moving the threshold up or down, we decide which samples are classified as positive. and which are classified as negative. And as we adjust that threshold, both the true positive rate and the false positive rate change. The ROC curve captures this entire story. It shows how TPR and FPR evolve across all possible thresholds. And more importantly, it reveals how well our model truly separates the two classes. In the next part, we're going to build the ROC curve step by step, by hand. Then we'll learn what makes a ROC curve strong, what makes it weak, and how to judge a model just by looking at it. Ready? Let's dive in.
In the ROC curve, the x-axis represents the false positive rate, and the y-axis represents the true positive rate. In our example, for the first threshold, we have FPR equals 0 and TPR equals 0.5. This corresponds to this point on the graph. At the second threshold, FPR equals 0.16 and TPR equals 0.67, which corresponds to this point. We repeat this process for all other threshold values. Finally, by connecting these points, we obtain the ROC curve. Now imagine we have a model where the score distributions of the positive and negative classes look like this. This would be an excellent model because there is no overlap between the two score distributions. If we set the threshold very high at the beginning, both TPR and FPR will be 0. Since no samples are classified as positive, meaning we have no true positives and no false positives, as we slightly lower the threshold, some high-confidence positive samples will be classified as true positives, so TPR will increase slightly. If we lower the threshold further, many more positive samples will be classified as true positives. Notice that FPR is still 0, because no negative samples have been misclassified as positive. Eventually, we reach a point where all positive samples are correctly classified as true positives, while false positives are still 0. As we continue lowering the threshold, some negative samples begin to be classified as positive, so FPR starts increasing. Finally, when the threshold becomes very low, all negative samples are classified as positive, and FPR reaches 1. This represents the ideal ROC curve for a binary classifier. In this ideal case, as we lower the threshold, the true positive rate TPR increases while the false positive rate FPR remains at 0. This implies perfect class separation. However, in practice, such perfect separation is extremely rare, since the score distributions of different classes usually overlap. Now imagine that the score distributions overlap. In this case, the model assigns high scores to some negative samples as well. When we lower the threshold, those samples are incorrectly classified as positive and become false positives. Therefore, as the threshold moves from this point to this point, the false positive rate is no longer 0. It becomes positive, even if only slightly. However, notice that from this point to this point, the increase in TPR is much larger. As shown in the figure, a large portion of the positive samples are already correctly classified, while the number of negative samples contributing to FPR is still relatively small. But when the threshold moves from this point to this point, many more negative samples are misclassified as positive. As a result, FPR increases sharply, and the ROC curve takes this characteristic shape. In weak models, where the score distributions of the two classes heavily overlap, lowering the threshold increases the false positive rate almost as much as the true positive rate. As a result, the ROC curve moves close to the diagonal line y equals x, indicating poor class separability. Now the question is, what is the weakness of ROC curve? In highly imbalanced datasets, the number of true negatives is usually very large. Because of that, even if the model produces a considerable number of false positives, the denominator remains dominated by Tn. As a result, the FPR can still appear small. This means a model might achieve a strong-looking ROC curve while actually generating many false positives. This is where the PR curve becomes important. In the precision recall curve, instead of using the false positive rate, we use precision, a metric that is highly sensitive to class imbalance. Notice that Tn does not appear in this formula. Therefore, when false positives increase, precision drops directly and often sharply, even in cases where the ROC curve may still look strong. This makes the PR curve particularly informative when the positive class is rare and false positives are costly. Notice that in the precision recall curve, unlike the ROC curve, recall or TPR is plotted on the x-axis, while precision is plotted on the y-axis. As we lower the threshold, recall increases. If precision drops sharply as recall increases, it indicates that a large number of false positives are being introduced. This is undesirable, because it means the model is sacrificing precision as quickly as it tries to capture more positives.
Thank you for staying with me all the way to the end. If you found this video helpful, please support me by sharing it with your friends and anyone who loves AI and machine learning. Don't forget to subscribe to the channel, and feel free to share your thoughts and ideas in the comments. I'd love to hear from you.